Today we are in the 9th lecture of the systems engineering, and today our topic is complex systems and system development process. So we are getting into the tools, and now we are getting into the different components of the system, and we understand the components of the system before we understand the tools, because if we know the components, then knowing which tool to apply on which component is easy. So the major learning objectives today includes the system hierarchy, or the order in which the different components of the systems are put together, system hierarchy, or it is the order in which the components are put together, then the building blocks of the system, or things that build the system, then the environment, the operation environment in which we are talking about, the environment in which the system operates. Then we talk about the interfaces and interactions. So these are the components slash subsystems. How do they interact? How do they interface with each other? Life cycle, from needs to design to field to retire slash redesign, like this. So the life cycle of the system. Materialization, which is like assembly and fielding, all those kind of things is part of this. And how do you do testings? So we go through all these major aspects one by one in this today's lecture. We'll get to some level and stop, and then we'll continue it in the next lecture. So the first question obviously is, why do you need to know the building blocks of the system? And before getting into this, we should understand that systems engineering requires broad knowledge of several interacting disciplines. So we are talking about, the concept here is the broad knowledge. Okay, we are not talking about not deep knowledge. Not deep knowledge like a specialist. Okay, so the systems engineer is not supposed to have the deep knowledge like the specialist. There's nothing wrong in having it, but a broad knowledge is sufficient. The idea here is, what is broad knowledge, or how do we define it? It is sufficient enough to recognize things, like many things that he need to recognize, that like program risks, technological performances, and performance limits. Then I'll write somewhere up here, interfacing requirements. Then we also talk about the trade-off analysis, among design alternatives. So the systems engineer should have enough knowledge to understand things like, or recognize things like, the risk of the program, technical performance limits, interfacing requirements, trade-off analysis among different alternatives, etc. So with this the systems engineer should understand the building blocks, because the insight on the structural hierarchy of a modern system is important. How does the modern system is structured? It is important. Okay. There are various types of building blocks in the system. Even to earlier things, people used to say that system encompasses the ultimate design, but nowadays we have what we call as, in military, many systems are connected to each other, or interconnected or networked. This create the new concept called system of systems. So, a classic example of this is like if you think about it, we have an AVAC system which is called as the advanced warning airborne radar systems. So, it will have the fighter jets underneath it, it will have the communication network, it will have the UAVs underneath it, it will have the ground guns underneath it. So, many stuff like that. So, it is where different systems, the fighter jet system, the communication system, UAV systems, ground guns, etc., they are all interfaced together to create a system of systems which will be an advanced warning system which is controlled by an airborne radar based system. So, using all of these, so the concept of systems have arisen, or SOS has arisen as well. So, it is very imperative to any systems engineer that we learn the building blocks of a system. What are the various types of the building blocks of a system? And when you know the building blocks, it will result something like this: facilitate lower working level of technical understanding. So, you would require the lower level of technical understanding which is necessary to decide on the technical trade-offs. So, what to use when you are making what to choose, this decision requires the lower level of working knowledge, and this working knowledge that we mentioned earlier, the knowledge that is sufficient enough to make multiple decisions. For that, the systems engineer need to understand what are the different building blocks of the system. In a complex system hierarchy, if you think about it, there is the systems, then subsystems, components, subcomponents, and parts. There are many classifications available, but this classification to a large extent gives a sufficient breadth and depth to do enough analysis into the aspects of the system. So, when we talk about the system, some of the examples of the systems include communication systems, There is also, we can think about it as the material processing systems or manufacturing systems. You can also think about as the aerospace systems. These are all examples of systems. Okay, and the major advantages of the systems are it should have properties of an engineered system. So, we are not talking about the natural systems or biological systems. Okay, not the biological systems or natural systems. We are talking about engineered systems. Okay, not, this is the keyword. And also the system should be capable of performing a significant and useful service. So, it should do a significant and useful service with only human and standard infrastructure as external lights. So, human, an operator, you can think about the human as the guy who is operating the system, operator or operators, plural form, and standard infrastructure. So, what involves the standard infrastructure? Typically things like highways, airports, then also we can think about it as fuel stations, power grids, satellites, etc. So, the system might use one of these standard infrastructure. The country will always have highways, the country will have airports, country will have power grids. So, the aerospace system would require to use airport. Similarly, like a material processing system might use the power grid for powering its machines. A communication system might use satellites, or it might also use the power grids as well. So, it will depend upon the standard infrastructure and human operators to perform a significant and useful service to the user or to the mankind. So, if you think about the system in that way, then subsystems, what are they? Some of the examples of the subsystems will be signal networks. Then you can think about it as, in the case of aerospace system, one example would be engines, aircraft engines. You can think about jet engine or turboprop or anything you want. You can think about databases. Okay. Then you can think about CNC CNC systems, something like this. These are all CNC controllers or CNC controllers. They can all be part of the subsystems. So what do they do is, it is a major portion of the system. So subsystems do form a major portion of the system, and it can perform closely related subset of overall system functions. So each subsystem system in itself may be quite complex, and they require several technical disciplines. So they are capable of performing the major task or major portion of the system functions. And what it is it can either also do a larger a subset of the overall system function to a good possible extent. So some examples, as I cited earlier, are signal networks, engines, databases, etc. Then we also talk about stuff called components. So the components are the middle level of the system elements. Earlier, components used to be were considered as equivalent to the lowest possible level, but now in this consideration we would actually look at as the middle level of system elements, with some of the examples being, let's say, in the signal receivers, database programs, database management systems. Then we can talk about a material reactors. We can talk about thrust generators, etc. So these are examples of the components. So they are middle level of system elements, and they correspond to configuration items. So they kind of do some major task as part of the subsystem. So like, for example, the thrust generator helps in the engines to generate the thrust, which actually provide the propulsion function of the system, aerospace system. So you can think about it that way. So the components to a large extent is the middle level of system elements, and to a large extent it is still have because earlier it used to be very few disciplines in engineering, but with this advent of this interdisciplinary engineering approaches, there are many aspects. So having a components as below the subsystem actually helps you to further create a functional hierarchy in the system, and you can apply systems engineering concepts into this. Then comes the next classification called the subcomponents, and some examples would include signal amplifiers, on CRT, or what we call as the cathode ray tubes. We can talk about it as gearboxes. We can talk about it as nozzles in the engine. We can talk about as the database libraries. So these are examples of the subcomponents which are critical to the components to deliver the function that it requires to ensure that the subsystem can perform an overall subset of the system functions. And when subsystems integrate together, they create systems. So all subcomponents, what do they perform elementary functions, and they are still composed of several parts. So a CRT, the elementary function is to do display equal to CRT, and it will have probably an LED screen, power module, a display controller, something like this. So it will have still many parts, but it will do one elementary function of display. So finally, if we talk about the parts, there are quite examples, like for example will be a transformer is a part, LED is a part, then seals, couplings, etc. These can all be thought about parts, which are elements that performs no significant function unless combined with other parts. So the LED might just glow, but unless you combine one LED with another LED and a control device, then only you will be able to get a display system or a display screen. So elements that perform no significant function unless combined with other parts can be thought about as the basic level of the parts. And then parts together become subcomponents, and subcomponents together becomes components integrate to become subsystems, and systems integrate to become systems. So if you think about it, in systems engineering at each level we apply different tools. So we have tools plus testing happening at each level. So we'll get tools plus test, keep on going. So at each level of integration we can we are ensuring that the system meets the functional the each level hierarchical level meets the functional requirements of the total system. So if you think about the hierarchical, this diagram is adopted from Kosaikov et al. In the systems engineering textbook. It is very famous and well known. So if you think about this system engineering as a discipline, so at the top level we have something called as systems. There are quite a lot of systems as part of it. Below that we have subsystems, as we seen. So some of them will be signals, as we said. We will have data, we will have energy, your materials, all those kind of things come along as part of it. Then your components. So this much divisions, usually you can think about it as the domain of a systems engineer. Below the components, there we have the some subcomponents like electronic, there is the software, then there is the mechanical, then there is the electromechanical, stuff like this. All these things we can group them together as subcomponents. So many of them will be here, and below the subcomponents we will have parts, quite a lot of parts as we seen before. So this area from here onwards is the domain of what we call as a specialists. So this is where the person would have very specialized knowledge in developing these parts and as well as the subcomponents where these parts integrate to. So in this place the knowledge of the systems engineer will be mostly in the form of a working knowledge, or what we call as sufficient, not deep. All these knowledges are associated with this part, but in this area where this is the systems engineer who drives this aspect as such. So this system hierarchical document should be kept in mind, because as we drill down from each level, we move from system to subsystem, subsystem to components, components to subcomponents, component them to parts. Remember we talked about iterative plus recursive. That aspect you can actually see here, and this is where we are drilling down to going to the lowest level and then building back up. So then you integrate back up from each level, doing testing and other stuff to make sure that the system comes in or system gets together or gets assembled in the way you want it to get it done. So then now we will talk about these building blocks of the system, and it is necessary that we need to understand this in a simplistic aspect. The reason why we need to do or learn the system building blocks, I said it earlier, but it is mostly towards understanding functional aspects of a system. That's the first part, and then partition it into a physical hierarchy. So when you understand the system, the functional aspects of the system, you might not have chosen the physical aspects of the system, but you might have just focused on the functional side. You say like, okay, I need this much range. You might not have specified on what engine and what fuel you are going to get the range. So then once you decide the range and other aspect, which is a functional aspect of the system, what physical component is going to get you that, realize that is where the physical hierarchy comes into picture. So the every system can be classified into two parts, in two dimensions. The functional dimension, where the functional aspects of the system is understood. Functional aspect of the system. Where does this comes from? from the user needs. What all functions the system needs to accomplish. This is the major aspect of it. Whereas the physical dimension on the other hand is what all parts plus subcomponents etc. should be used to realize the system that can perform desired functions. Okay. So, then once you know the functional dimensions, then you can choose the physical components accordingly. And once you have the physical components, then all you need to do is worry to integrate them in such a way that the functional dimension is met. So, each dimension can be partitioned into its elements. So, the functional dimension can be partitioned down for what we call as we can recursively and iteratively partition it into its elements. So, how do we do that? We will actually see this. So, let us first talk about the functional building blocks of the system and then we will talk about the physical dimensions. So, the functional building block of the system, you can talk about it as it basically can be classified into three major things. Okay. So, there are like three major classifications. What are those three major classifications? That is information, energy and materials. Okay. Almost everything that you want to do with any system can be classified into this. So, the information is, if you talk about what is information, let us define information as that aspect, the functional aspect that contains all knowledge and communication. It should also be noted that it is the largest chunk in any system, largest chunk or portion of any system, and hence it needs to be classified, hence further classified. What are they further classified into? They are further classified into two. They are data elements 1.1 and signal elements 1.2. So, what is the detail? Let us talk about data elements. Data elements, it basically they are the elements, functional elements that deals with all types of stationary information. So, things that are to be stored, that are available stationary, not changing over time. So, stationary means do not change over time. As time progresses, the data does not change as much, or they are kind of stored in a hard disk or someplace where you are accessing it. Whereas a signal on the other hand is they are the elements that related to information propagation. So, mostly the data elements is from where you use data elements to generate information, and this information if you want to propagate, then you use the signal elements. So, that is how the data and the signal elements are the subcomponents of the information building block, which is a functional building block. If you talk about the energy, then what is the energy? We can define it as the it is that part that energizes the system and ensures movements of all system components. In simplistic terms, is the one that provide power. Power is a loosely term, but this is a colloquial usage. Okay. Some people say that energy is the one that actually provides the power for the system to do the work, or the capability to do the work. So the energy elements, then we talk about the energy elements are the one that provide energy and motive power. So anything, it could be an engine, it could be a battery, it could be a like fuel cell, doesn't matter. So some of the aspect, any aspect, it could be a thermocouple even, or it could be light source, optical source. Anything that actually provides energy or motive power for the system so that it energizes the system and ensures movement of the system components. That is what comes as the energy, which is the second functional building block of the system. Then we have the materials, which is a substance of all physical objects. This is how you actually make the thing that is forms the skeleton of the physical system. Doesn't have to be skeleton, it can be everything else. Skeleton plus others, all of those aspects are part of this. Then what are the elements, material elements? So they provide structure to the parts, subcomponents, etc. And they also do transformation of materials. So you might have like raw material in the form of metal, but you might melt it into a molten form, and then you cast it and create a particular part which could be used as a casing for an engine. Then that would be component of the material elements of the system. So the materials, energy and information are the three functional building blocks in which the information is classified into data and signal elements, and energy has only energy elements and material has material elements. And we have broadly seen what are some of the aspects that constitute these functional building blocks as part of the system. Now, we also need to talk about the functional element criteria. And the functional element criteria, to a large extent, if you think about it, it has three aspects. But the functional element criteria, it ensures that no element is not trivially simple. No elements is not significantly complex, and it has wide applications. Remember, we told about that the criteria that we use, the significance, singularity and commonality, these are the three criteria, 1, 2 and 3. We use these criteria to ensure what? No element is not trivially simple. It's not, so we ensure that it's just not that simple, because sometimes the trivially simple things, you might not need to go through all these type of analysis. And we also want to ensure at the same time that they are not significantly complex either. So as I said earlier, it is the balancing. So this is where the balancing aspect of systems engineering comes into picture. So first we talk about is the significance. So the significance can be defined as the each functional element must perform a distinct and significant function. So each functional element must perform a distinct and significant function, typically involving several elementary functions. So what we are interested in here is that the significance of the functional element. Each functional element must perform a distinct and significant function, typically involving several elementary functions. So this is where you actually do the balancing. What is the distinct and significant function that we choose out of that? Then the singularity aspect of this is each functional element, what does it do? Should fall largely within the technical scope of a single engineering discipline. So, this is where the singularity aspect of it is. It should also be, functional element should be in such a way that it should be within the scope of the technical scope of a single engineering discipline. So, the interdisciplinary components, we are further breaking it down into a level so that individual engineering experts, individual engineering discipline experts can actually take care of the technical scope of the functional the element. Then the last one is the commonality, where we basically say that the functions performed by each element can be found in a wide variety of system types. So, if somebody says I have a solar photovoltaic power system or power subsystems, or you can say power component, whatever you want to call it, then this is a functional element because it actually provides the energy element, and it is an energy element because it can be found in a wide variety of systems. You can find it in the household systems, you can find it in satellites, you can find it in an automobile, you can find it even people using it for charging mobile phones. So, you can see in wide varieties of system types, you could see this function being performed. But that just doesn't is not just sufficient enough. That's one aspect. It should also have singularity, it should also have significance. All right. So, we move to the next aspect, which is the system elements functions. So, what are the functions of the elements that we talked about? So, the data elements and the signal elements, as we said earlier, these two combined together, that is part of the information, and then the material elements and the energy elements are part of the material and energy functions. So, here is so this is the classification. So, what are the major functions of the data elements? So, the major functions, some of them you can list about it as analyze, interpret, organize. You can also do querying, you can also do convert, project, project what? Data and information into required formats by the system and users. So, the data elements, the function is to analyze, interpret, organize, query, convert, project data and information, that is the critical part, into the required formats by the system and the users. So, that is the major function of the system, the data element. Whereas, on the other hand is a signal element, the functions will be to generate, transmit, distribute, receive what? Receive signals for sensing and communication. So, here it could be, instead of signals, it could also be information, it could be commands, whatever. Okay. So, from the data, the information can be generated, or a user might have given an instruction which through which, when it passes through the signal element, it will generate the signal, transmit the signal, or distribute the signal, it will receive the signal, so that the communication between different components of the system are possible. The material elements, what do they do? Their functions will be to provide structural support, it also create enclosures or boxes or packaging, it can create the shape transformations, like cylindrical metal to gun barrel, something like this will be an example. Then you can also talk about the location where all the strengthening is required, and it also can involve the composition, composition of material substances. These are all parts of the or functions of the material elements of it. So they provide structural support, they create enclosures or create packages, they allow for shape transformation, they do for locations, which is like sometimes it's also can be thought about as strengthening is also one part of it, etc. like that. Okay. About energy elements, what do they do? They provide energy, they can convert energy or power the system. So there can be multiple ways you can provide energy or you can convert energy or you can power the system. So it can generate and as well as generate also is another way to think. It's a colloquial way of thinking about it. So now we talk about the physical building blocks. So the physical building blocks to a large extent, they are the embodiments, the physical embodiments of the functional elements. So once you identified the functional elements, then how will we achieve the functional capabilities? This is the this is where the functional physical embodiments of the functional elements in the form of hardware and software. Okay. It can be hardware because that be here it will be a physical component, and in a software we can thought about it as a logical component also. There could be other components as part of software as well. There are many distinguishing aspects, okay, characteristics. Some same distinguishing characteristics, the significance, singularity and commonality that we discussed earlier in the previous slides. So if you think about this, we talked about it here, the significance, singularity and commonality, which are part of the functional elements criteria. They are also applicable to the physical building blocks or the physical elements as part of this. And the they're also they're typically called as component elements. That's where sometimes people use the word components, and then this gets confused with the components that we saw in the functional the system hierarchy. So they are the component classification in system hierarchy is different compared to what we talk about these component elements or these colloquially components that many of the people in the system design process use. So these are two different things. Here we are talking about the physical stuff, there we are talking about the functional aspects of the system. So the so to a large extent, how does this building these physical building blocks, the classification of physical building blocks are based on, they are based on what? On different design disciplines and technologies. So remember we said earlier that the elements, one of the aspect is the singularity or should fit within a single engineering technology field. So that aspect is also there. So the physical building blocks are classified based on different design disciplines and technologies. Okay. So depending upon the design disciplines, we have different type of components, or the technology that are used also defines the different discipline compounds. So once you have the functional elements, from there we try to create the physical elements or the physical embodiments, how that will help in achieving the function. So what are some of the common elements? So the common component elements are electronic, electro-optical, electromechanical, mechanical, thermomechanical, and software. So let's go through each one of them with few examples and see what are their typical functions. So the electronic elements, when we talk about it, the physical elements or the component elements. So here we are talking about the physical. Okay. So the electronic one, that will be it will be a receiver. It will be an example. Transmitter, another example. There could be a signal processor, okay, etc. So these type of component elements which will achieve the electronic functional capability, or it will provide the electronic functional capability, is what is classified as the electronic components or the electronic physical components. On the other hand, when the electro-optical ones, their major job is to do a sensing, like the electro-optical camera or the IR camera, infrared camera. These kind of things are part of the sensing. Then they are also part of is the display, like CRT, LED, they are all part of that. Then we also have what we call as the optical power. So optical power, one example of this would be our photovoltaic PV, solar, what we call as the solar cells. So they are all part of the electro-optical systems. Then we also have is the electromechanical systems. So some of the electromechanical systems involves inertial systems. So in aerospace, we actually use as INS, inertial navigation systems. They are classic example of electromechanical systems. There are transducers, okay, like example pressure transducers. They use pressure, or they measure pressure and convert that into an electric signal or a voltage or something like that. And another example of electromechanical device is a data storage, or classic is HDD, hard disk drive, because we know that there's a hard disk is designed something like this. You have a spindle on which multiple multiple discs are created, where, or magnetic discs are there, on which HUD moves and writes different type of data on that with the help of electro, depending upon the signals that is given to it. Different bytes, zeros and ones, get stored on that. And there's a motor the below that actually spins this spindle, in which these discs actually rotate at a specified speed, and then they write on the top of that. So these kind of a system. So this, when it is put in an enclosure and other things, it becomes an HDD, hard disk drive, which would be an electromechanical component of a computer system. So another example of it is, another thing we talk about is the mechanical systems. So what are the mechanical systems? They are examples of it is like framework, there are containers, material processing machines or machining systems like lathe, drilling machines, etc. They are all part of it. So there is some mechanical power, some motion happens, and using which you apply a force to create to remove material, so that you can do the process the material to create something like a container or a framework or a specific part that can be used for assembling maybe electromechanical or electro-optical components, and then joining them together with other things. That's all part of the integration into a system stuff. Similarly, there's a thermomechanical example also, which is typically you can think about as a jet engine is an example. You can also think about as a rotary engine is also an example, which is a turboprop. That's an example of it. There can be example as cooling units. There can be examples as the heating units or heat exchangers, etc. These are all part of our physical component elements of the thermomechanical, which also form together to create the to realize the functional elements of the system. And finally, with the software examples can include operating systems, which we called as OS. Then we have applications. One applications could be DBMS, database management systems. You can also have firmware. So if you have a display driver, a display card, then a driver that is used for this, okay, drivers and stuff like that are part of the firmware. So the you can see that the physical components are can be classified into these 1, 2, 3, 4, 5, and 6 parts or 6 buckets for easy understanding and study and kind of stuff. But the systems engineer, what he is more interested in these main issues. What are the main issues he is interested in? They are reliability, reliability of these parts, reliability, form and fit, what is the shape and how will they fit, and the compatibility with operating environments. So where the system operates, will it be able to work? Like for example, if you are trying to create a electro-optical part which does not work in a moisture area, and you are trying to design a naval system, then it will not work. So you have to ensure that the element, the physical component element actually is compatible with the operating environment of the system. Similarly, there is maintainability. How hard is it to maintain it? Then there is a producibility. Is it easily producible or is it available? It can be mass produced. There is a testability. Can the component element can be tested, or the physical component element can be tested and validated that it is producing, doing what it's supposed to do. Is it safe? Safety is another example, another aspect. Cost is another aspect. And more than that, on top, it should not is the key word, should not violate integrity of the functional design. So you could actually create a rocket engine that could be mounted onto an unmanned aerial vehicle, which would have sufficient thrust to take it off. But then the takeoff aspect might do, but it might not provide the endurance that the UAV is expected to do. So then it's not whether it can do just the function of taking off the UAV. It should also be able to take care of the functional design. So we used UAV as an example in many times. So it should not violate the integrity of the functional design. So that's where you choose. So this is where also the trade-off or choice decisions comes out. So with this, today we conclude our lecture, and in the next class we will talk about the additional aspects of the system environments and how do we study the interfaces, integrations, those aspects of the system, and then we will move into various tools that will help us to realize these kind of things. Thank you very much for your patient listening.